Well, welcome back, folks. Looks like it's time to get started. Let me go to this document here. Okay, I don't have a ton of announcements today, but we're pretty much done with the course after today. We're going to finish off section 6.7, just a little bit more work on dealing with exponential models for growth and decay. Then after that's complete, we'll turn to reviewing on this document for Thursday's review. Probably we'll start that on Thursday, but we'll just see where we end up going through 6.7. Then that takes us to finals week. It'll be on Monday, less than a week away since we're on Tuesday. It'll be Monday, December 11th from 3 to 5 p.m. I'm on the wrong spots right there. And aside from that, it's going to be pretty typical rule set. It'll have open calculators. TI-30 X2S is definitely a good choice. It is closed notes, but like we mentioned before, this document here will be actually provided on the final exam. It's a good idea to print it. Maybe not this one. This is just the first cover sheet. It's a good idea to print this, the formula sheet, just so you can use it while you're studying. You'll familiarize yourself where everything is on that formula sheet, how it all works together. And this will be provided on the real final exam. It's 2 pages, and it's got pretty much all of the nasty stuff you would want on a note card anyways, provided here. Well, any other questions, folks, before we get started with today's work? Okay. Maybe one last thing before I forget. I'm going to add another description here on the Moodle website. I made a little reminder for myself. The last day to work in ALEKS itself, it's going to be 11:59 p.m. on Monday, December 11th. So essentially the end of the day of the final. But also I'm accepting late quizzes. So if you have any quiz that you completely missed, which is easy to do, especially on the last few of them, I'd say, I'll accept them for full credit. The final due date on late quizzes will be Monday, December 11th. And I'll edit the website here to reflect that as well. Well, any questions, folks, before we get going? Okay, well, we're in section 6.7, and here's what it looks like. Some of these problems are actually going to look almost like deja vu compared to what we did before. They're very similar. They just have a little bit extra follow-up type questions. There's an emphasis now on equation solving involved with these models. And I did make some changes on this on December 2nd. The changes are way down here. I copied these formulas from a different document where R was given as K. So if you see a K there, if you've already printed it out, change that to R and you're in really great shape. It's kind of a weird revision to have to put in there. Let's go back up to the top. First thing they give us is a reminder about the compound interest formula, but we were just looking at a formula list. Let me take a look at that one. Compound interest is probably, if it's provided at all, let's take a look right here. So interest compounded n times per year. You could use this formula if this one really was a final exam question. So take that information, or you could visualize it this way. And first thing we should do is start summarizing what we know. It says Keith deposited $4,000 into an account. So this amount right here, we think of as an initial amount. And so it's going to go right here for the principal. So we'll have amount at time t is equal to 4,000 to start. Then it'll be 1 plus. Next thing we need to find is the rate R. But it says it's going to be at 2.4% interest. So we'll take this number here, plug it into that location as a decimal. So that's at, let me fix that fraction first, a 0.024. So we've got our numerator there. Next thing we need to find is this value for n. And it's going to be the number of times that we compounded. And it says here, Keith deposited 4,000, 2.4% interest, and it's going to be compounded quarterly. That just means we're compounding 4 times per year. So 4 goes down below. Then it also appears in this location when it's multiplying the variable. So we'll have a 4 times t in that location. So this is a good start. This is the entire model that we're going to be working with next. It says, assuming that no withdrawals are made, that's a pretty similar assumption, common assumption you'll see on these problems. We want to know how long it will take Keith's investment of $4,000 to grow to $100,000. Kind of like what we did on the end of the last class on Thursday. This is a strange question because Keith only invested $4,000. That's not a lot. The interest rate is very low. Your money is essentially rotting compared to the interest or inflationary rates. But still, we want to know how many years to get to 100,000. So in other words, the question is this. We need to solve an equation that goes amount at time t equals 100,000. Doesn't hurt to put the unit in there either. So it's handy to have the model right above. All we're now going to do is put 100,000, leave it exactly where it is. On the left, a of t, we'll just substitute in the entire model. So here's 100,000. I'll drop the unit at this stage. Left-hand side is going to be the 4,000. And because we're going to be equation solving, it's a good idea to just jam all this into the calculator. Watch out for these statements here. This is more for Alex than anything else. Alex wants a very, very accurate answer. And it makes sense. This is money. People don't want their money to be shorted after investing. And so we're not going to round anything in the middle. So good thing we're dividing by 4. This will come out as an exact answer. So for this little calculator here, pretend this is a TI-30X2S. I'm taking what's inside the group and just taking 1 plus 0.24, 0.024 divided by 4. Let's throw in a value of 1.006. So 1.006 goes in to the power of 4t. So our goal now is we want to solve for t so that we get the $100,000 on the right-hand side. First thing we can do is just divide by 4,000 into both sides. So grab the handy calculator again. We're taking 100,000 from this side, divide the 4,000 into it. So we'll get exactly 25. So next step is 1.006 to the power of 4t is now exactly 25 after dividing. To get that value for t, all we're going to need to do next is knock 4t out of the exponent position. And there's always a good way to do that. You can use a logarithm to start. It would read natural log of 1.006 to the power 4t is now natural log of 25. We have to use the natural log on the left-hand side so that now this portion, 4t, by properties of logarithms, comes down as a coefficient on the very, very next step. But that forces a logarithm on the right-hand side. What we do on one side of the equation, we're just forced to do on the other. So here's our next step. 4t has come down as a coefficient. It's still multiplying the natural log of 1.006, still equal to natural log 25. But if our goal is to divide, or excuse me, solve for t, we're just now dividing by 4, natural log 1.006. So let's show that step here. 4, natural log 1.006. 4, natural log 1.006 as well on the right-hand side. Let's just show those cancellations here just for helping with visualization. All that's left is t on the left-hand side in years. And on the right-hand side, we have the exact value right here. If this was a real final exam question, and even if you made a mistake in the calculator, let's suppose it's 10 points, you would get 9.5 points out of 10. So as long as this is here, this is where almost all of the credit is, the exact answer. Approximation is still important. We have to get a value out. And I mean, that's a good step anyway. If we can tell if it's reasonable or not, just by seeing what the value is. If this comes out as 3 years, I'm not going to believe it. There's no way $4,000 grows to $100,000 with that interest rate in just a few years. We're expecting a long time to get to that amount. So back over here, we're putting in natural log 25, so ln 25. Immediately put in division, and your entire denominator has to be 4 times natural log 1.006. But in the calculators, you might need an extra parenthesis to contain all of that in the denominator. So 4 natural log 1.006 gives us this quantity in years. We want to round to the nearest 10. So that would be 134.5 years. Probably Keith is dead by then, but at least there's $100,000 in the account. So 134.5 years. That might cover the funeral costs and things like that. Who knows? Well, we got it, folks. That's the exact solution on this problem here. Honestly, the trickiest part is definitely in the calculator, and it's frustrating because if you're studying this topic in ALEKS, they're going to be a real badger about this problem if we don't get right to 134.5. So the things to watch out for is you definitely don't want to approximate natural log 1.006 at this step. You only want to approximate this exact expression right here. And if it's not coming out right in your calculator, what it should look like is, I'll put here for the calculator, it would be natural log 2.5 division. We'll need a parenthesis to keep everything in that denominator. Then 4 natural log 1.006. Two close parentheses on the right, and that's probably what it should look like on your screen. If you execute this, you should be getting 134.5 after rounding. Does that look right to folks for answers so far? Awesome. Again, Alex is going to be the real jerk about this, not getting the answer right. But if you follow the process, only use your calculator in the last step, you're probably going to be in really great shape. And the final exam is very low pressure with the calculator. It's more just an opportunity to get the approximation here and check if it's reasonable. If you make a mistake, you still get most of the credit on that step. Well, we did it, folks. That's our first model we got through for the day. Any questions at all so far? Okay, so we're not done with Keith. There's a second example we're going to work with. This model is kind of nice. It works great for compound interest and all that kind of stuff. But what we really want to do is work with the exponential model. That's what n is going to get larger and larger. And this is what it's going to turn into in the next step. We'll look at the continuous growth decay formula. This is where the notes are really going to be mostly involved with. The model is a times e to the power of RT. Let's make that just slightly bigger. Here, we'll say that a is going to be the initial value. As far as initial values go, it's the same as the principal amount that we put right here. Next, we have a rate R in this location. R is going to be the continuous growth rate. If it comes out positive, we have continuous growth. And if it's negative, we'll have continuous decay instead. Essentially, that's pretty much all that's going on here. But one thing we do have to recognize whenever we're reading a problem, say in ALEKS or on a final exam, is we need that information right there. They don't say continuous growth or continuous decay. It might be a different model we're using, maybe this one up here, for example. The moment they say continuous growth or decay, that's when you're taking a base E right here and using this formula. So there's a bit of a vocabulary recognition for all these problems when you see this here. Aside from that, this is something we've used before. We're just going to practice with it a little bit more. So here's our example 2 for Keith. It says this time, suppose Keith is also considering an account that earns 7.2% interest. So that's a little bit more appropriate. That competes a little bit with at least inflationary rates. It says it's compounding continuously, so that means we're using this model right here. In fact, the moment you see this, it's not a bad idea to just write down right away from continuous compounding, we'll have amount at time t equals a times the base e exponential to the power of r times t. Well, we could have plugged in some information. We know the value of r is at 7.2%. Still has to be converted to a decimal, so r is now 0.072. Now, what else do we have here? It asks us what amount should be invested for Keith to have. He's still going for $100,000 in this account in 10 years. So Keith is not happy with 134.5 years. We're going to try to move the time frame down to 10 years on this thing. But when it says what amount should be invested, that's A right here. A is missing this entire problem. Our goal is to find that initial principal amount A. So right here, A equals unknown, just a question mark, just a reminder, our goal is to solve for that value. And let's see what else we have. Keith wants to end up with $100,000 in his account in 10 years. Let's keep this one conveyed in gray. So in other words, What Keith requires is this. The amount in the account at 10 years has to be 100,000. Let me try to put a unit on that. So that's the walk through the problem so far. You'll see these a lot on these problems. We're not going to try around any intermediate computations. If you do, that's okay. Just keep lots of extra decimal places to be extra safe. Sometimes it's a little bit more tedious than just writing down this exact step, honestly. And then we'll round our answer to the nearest step. Okay, so we want to know how much to invest so that after 10 years, Keith has $100,000 in the account. The only thing we get to work with is this right here. The only thing we can plug in is the interest rate R. So let's make that our next step. Amount at time t is the unknown A times e to the power of 0.072 times t. Sorry, say again. Oh yeah, so we're going to plug in this next at 10 years. So after this line, what I would write down right below it is, well, amount at time 10 for the years there, we're going to have 100,000. And then we're taking this 10 and plugging it right into that location there. So you're probably just a step ahead of me there. This middle step doesn't necessarily have to be written down, but if it helps out, it's kind of like connective glue from one step to the another. Other questions so far to this stage? Okay, well, let's plug in everything we've got. On the right-hand side, I've got 100,000 still. On the left-hand side, we're plugging 10 right into this location and carrying in everything else. So here's A, the unknown, base the exponential to the power of 0.072 times 10. So 10 goes right into that location. That means we can take maybe one additional step to simplify here. I meant to zoom out for a little bit more space. We have base A, e to the power of 0.072 times 10 is going to give us a 0.72. That's still equal to 100,000. With a little bit of space after that equals right here. Again, our goal is to solve for A, and that means, I'm not sure why I gave a little bit of space here. I think I might have been thinking I was going to take the natural log of both sides, but we have no call to do for that this time. If you want to solve for A, just divide by e to the power of 0.72, and we're home free on this. So this one's kind of an oddball. This one is motivated by something I saw in Alex, so think of this problem as covering all bases. This is a weird question that can come up. So the amount A to be invested will be, take 100,000, divide by e to the power 0.72. And here's what that would look like if you put it in the calculator. In the TI 30x2s, it would look about like this. Unfortunately, no commas allowed for the calculator. It wouldn't know what to do with it. A division, then you'll have an e to a power 0.72. So it should look about like that once you type everything in. In Desmos, it looks a little bit different. And we'll get 100,000 divided by e power 0.72. And it says Keith needs to invest about $48,000, 675, and we should round up 23 cents. 48, 675, 23. Let me double check my numbers here. Okay, I think I copied it down, but how's that look to folks? Are we all getting about the same figure so far? Is it rounding funny on your calculator? Can I take a look there? Oh, weird. Yeah, you might have to control, I think it might be like a float option or something like that for the numbers to display on it. Yeah, sometimes those calculators, are almost too smart. They just decide they know what's best when it comes to rounding. They do their own thing. Other questions so far? Okay. Did it work out? Awesome. Well, Keith is going to have to come up with $48,000, but at least that's appropriate. The timeline is only going to be 10 years. And it wasn't so much because of this model that it was growing continuously. It was more the rate was way, way better at 7.2% than the prior problem. I think it was like 2.4% or something. That one was, yeah, 2.4%. Well, that's a couple questions with compound interest. This one's a little bit of an oddball one, but occasionally we have to solve for a rate or an initial amount or for time. There's lots of different things you might have to solve for in these kinds of problems. Let's try out another one. For example, 3. Looks like we're still dealing with money, but we won't stick with money for the whole way down. Money's a great way to start for these things because the models are abstract, but money's intuitive. We use it every day pretty much. Yeah, go ahead. Yeah.
How do you get to the 0.72 instead of the 0.072?
Oh, right over here. That was the times 10 right here. And pretty much the way I visualized it, if you're multiplying by 10, I just took this decimal point and shifted one spot to the right to get the value below. Other questions at the moment? Okay, let's try out this next one then. One moment, the document is not responding. There it goes. Computer must have been updating or something. So here's our next scenario. It says the amount of $230 is invested into a savings account that is compounded continuously. So we have two things here. Looks like that's our initial amount. Compounded continuously is giving us this model. An amount at time t is going to be some initial amount a. We'll plug that in the next step, times e to the power of a rate times t. So we've had that information so far. They say next, assume no withdrawals are made. After 4 years, the account balance is $243.38. Let's write that down right away, just so we have it. So the amount at 4 years came out to be $243.38. So that's the sentence right here that gave us that line. Next line, it asks, what is the annual interest rate? So this time, the unknown is going to be R, and it's our job to solve for the interest rate in this problem. Guess we ought to highlight this portion right here. So here, the question is, what is R? And you don't have to put that down there, but sometimes it's a good idea to put something like this as just as a reminder. Once we find that, the whole problem is over. That's the whole goal of the question, essentially. It says next, don't round any computations and round the final answer to 4 decimal places. And this came from Alex as well. After we round it to 4 decimal places, and only after we round it to 4 decimal places, then we'll convert it to a percentage. That's what they want as their official answer, which makes sense. If you're giving someone an interest rate, they're expecting a percentage typically. But in computation, it has to be written as a decimal to start. So that's what we're dealing with. And really the only thing we can plug in is this value here right here. They gave us an initial, our principal amount of $230. So $230 grew to $243 after 4 years. That does not sound fantastic. Probably sounds like another Wells Fargo savings account, probably like a 1% interest rate. We'll find out what it is exactly once we update this model just a little bit. Amount at time t is put in the initial amount, 230. Then it's e to the power of r times t. T we're going to fill in because of the next step. We're going over here where it says, well, if the amount at time 4 years is $243.38, then we can plug the 4 years right into that time variable, and that's going to be our whole left-hand side. It'll come in as 230 Then take your base E exponential to the power of R, gotta highlight that one, times 4. And that's set equal to $243.38. So I haven't done a ton of this so far on this step so far. All I've done is taken this, because we have the model right here in its most update form. I plugged 4 in to get that output down below. Might as well connect that thought with that highlighting there. Any questions, folks, to that stage? Okay, this is usually the hardest part of the entire problem, just setting up everything, getting the information, getting down to the equation. If you make any mistakes at this stage, it's not the end of the world too much. As long as you have an equation similar in spirit, if you solve it using all the correct steps from here on out, even if it's the wrong equation, you still get a great deal of partial credit for this kind of problem, because a lot of the credit is just solving the equation after it's set up. So let's go to solve this. We want to solve for R right there. Might as well divide by 230 to start. But here's where it could go wrong in Alex specifically. Alex wants a really, really accurate answer. And so if we took the 243.38 and divide that by the 230 from the left-hand side, if you want to get the answer that Alex is expecting, you'll probably want to carry down maybe 6-ish decimal places of accuracy just to make sure it comes out right at the very, very end. And honestly, that's tedious enough. It's more efficient to just go e to the power of 4r equals, divide 230 into 243.38. I'm just going to keep it like that in its exact form and only shove everything into the calculator when we're at the very last step. This is easier to copy down than copying down a bunch of random digits, I'd say, right here. Well, we're just about there. Our goal is to solve for R. I keep forgetting to color code that, but we'll just smack it with a highlighter. Anyone know what the next step might be if we're solving for R right there? Good call. We want to eliminate the base E exponential, so natural log on both sides. And even if there is a net base E there, notice the natural log is still extremely effective. When we had to solve for 4t here, we just took the natural log because it liberates 4t, drops it down. Here it's even better. It's the inverse function. So it doesn't just liberate 4r, it eliminates e as well. So let's write this as our next step. There'll be natural log of base e to the power of 4r. Hey, remembered this time. Is equal to the natural log of 243.38 division by 230. Then here's our reward for studying logarithms. All of that's gone, and we get 4r is now set equal to the natural log 243.38 divide by 230. And that means we're essentially there. Divide by 4, just an ordinary algebraic step. And the interest rate R is natural log 243.38 divide by 230. And I'll write this about what it would look like in an actual calculator. Typically, algebraically, I'd write it like this, still the right way to write it. But if it's going into the calculator, it would probably look like this instead, all in just one line. So that's our value defined. And we have the exact value. Next, we're going to approximate it to 4 decimal places. So R is, let's take a look. We're expecting a small interest rate because the value of 230 initially barely grew at all after 4 years, which is a significant amount of time. It's always good to kind of look at that and imagine what it should be before we even calculate. That way we can tell if there's an error here. It's not like a 20% interest rate or anything like that. The natural log, 243.38, divide by 230, still inside the logarithm. Then close that parenthesis, divide by 4. And to 4 decimal places, it's a 0.0141. That didn't even round up to a 2. 0.0141. So now we've got our approximate answer. The last thing they want is this value as a percentage. So just shift the decimal 2 places to the right. Or if you like, you could visualize it this way. times 100% is the official way to change the unit there, and you'll get 1.41%. That's not completely accurate. We did round this to 4 decimal places, so we're actually leaving some of the interest rate on the table there. But that's an approximate answer, which is pretty accurate still. We did it, folks. On the prior problem, we had to solve for the initial amount. That was not too bad, but if you have to solve for interest rate, you do need the natural logarithm to get through that problem there. Well, that's another problem down. Let's example 3 already. All these are really kind of similar. The only thing that's changing from problem to problem is different things that we were solving for. Any questions at all, folks? I'm running through this one. Okay, so we've been dealing with exponential growth models. All of them so far have just been money at the moment. When we go down, handy formulas start to show up. And now we're going to look at dealing with things are decaying exponentially or growing exponentially, but not necessarily money any longer. This is where I made some revisions on the notes. I had K here, but I put it in as a R instead, just to match what we're actually seeing in the book. The book is using R rather than a K value. So it says for the handy formulas, consider again the continuous growth decay model A of t equals e to the power of RT. So we can bump that up. So the formulas are only relative to this model right here. And it says, if R is positive, you're dealing with continuous growth. And one of the big things we're interested in for continuous growth is the so-called doubling time. And doubling time is really actually easy to find. It's the natural logarithm of 2, the 2 there is for the doubling time, divide by the interest rate. If you wanted, you can solve this for R, and it's just natural log 2 divided by doubling time. So that's kind of interesting and handy. And one thing that's kind of curious about this is when it comes to doubling time, notice one thing that's not in this formula at all. The initial amount A makes no appearance. And that causes some confusion in some of the problems you might see in ALEKS, where they'll give you a lot of information. You don't even need A when they ask for doubling time, but they provide it other anyways, just to see what we'll do with that. So let's make a note here. For either one of these formulas, the initial amount A is surprisingly, in a way at least, not relevant. Is not relevant. So some problems in ALEKS are just literally asking you your doubling time. You just take natural log 2, divide by the interest rate, and you're completely done. Now, if R is less than 0, in this case, we have things that are decaying exponentially. Maybe a radioactive isotope or something else in nature. And what we have instead of a doubling time is a halving time, or half-life is what we typically say. Half-life is kind of weird how our book decided to indicate it. They just write it out, that's half-life. And I mean, that's not bad or anything, but you should know that there is a very common symbol for this. It would be the Greek letter lambda. I'll put it here just for reference because it is definitely something you see a lot, just not in our particular textbook. But hey, our book was free, so we got that at least. Typically, you'll see lambda is the symbol for half-life. I'll write it out here, just like it does, we see in the formulas and the book as well. And the way it goes is half-life almost looks like the same formula, right? But it's negative of natural log 2 divided by R. And if we want to solve for the decay rate R, it'll be negative of natural log 2 divided by the half-life. Now that negative is curious, but there's actually a pattern to this. If we were talking about doubling time, there should be a 2 here. If we're talking about half time, so half-life, there should be 1/2 here, not 2. But that negative is the key to this answer. Negative of natural log 2, by properties of logarithms, is the natural log of 2 to the power -1. The coefficient here can turn into an exponent, and now 2 to the power of -1 is 1/2. You can make the negative exponent forced to be positive by throwing it down to the denominator. Now it has power 1, so it goes away. So one thing that's almost kind of a disservice in a certain sense is this negative natural log 2 is the standard way to write it, but this makes a little bit more sense. You're obviously dealing with half-life if you see 1/2 there. Just some weird little fact about how things are written. I'll keep it in this way because once again, it's almost confusing to go to this formula that makes intuitive sense, because this formula is almost always the one that's being used. So these formulas here are definitely very helpful. And now that we're looking at these formulas, let's take a look at one extra thing. Are these actually in the notes anywhere? Let's see. We have information about exponential formulas. I don't see anything about half-life or doubling time. I would say these are good formulas to have memorized for the final exam, just in case a question like that comes up. They're really fast formulas. They only differ by a negative sign. And if you have that formula, sometimes, like this says, you can save a ton of steps just by using this information here, rather than running through a full process if we forgot the formula. So let's make a notice here. They're not just handy, but these are important to memorize for the final exam. And when we review for the final exam, I'm going to try to pay special attention to what formulas are provided and which formulas that we will have to have memorized and ready to go when we go to take the final. So with all these formulas ready to go, let's give this a try. We're dealing with plutonium-239. So this looks like missile bomb making type material. So this is the nasty kind of stuff. We're told that the half-life of plutonium-239 is 24,110 years. I don't know why I didn't put a comma there. Just slightly more readable. So we're dealing with plutonium-239, and now they ask us, how much of a 25-gram initial sample, we might as well highlight that, will remain after 5,000 years? We don't want to round any intermediate computations, and we'll round our final answer to 4 decimal places. So that's what we're dealing with on this problem right here. Let's start off by just writing down the model. Let's see. If you or see anything that indicates half-life, the only possible way half-life appears is if you're dealing with this model right here. So already this is the key word to tell us we're dealing with an amount at time t equals a times e to the power of r times t. So there's our model. We know the value of a, so we can plug that in. But what we really need is the value of r. They gave us half-life to be 24,110 years, and that's pretty much half the story in getting the decay rate. So start by saying half-life equals 24,110. Then this formula right here, you could plug it right here and solve your equation for r, or this formula on the right is just as valuable as the one to memorize. This one gives you r straight out. We'll say r is now negative natural log 2 division by 24,110. So now everything is set here. We have the value of a, we have the value of r. Next step I would take is just update the model with our known values. So the exponential decay model for plutonium-239 is now amount at time t is our starting amount of 25 grams. I'll just write it in as a 25. Euler's number, the base exponential to the power of r. It's kind of a nasty r to work with, but it is what it is, times t. Let me see if I can format this a little bit different. Hey, just barely can get that in there. So here's the value for r. Negative natural log 2 over 24110. And then that whole thing is multiplied by t. Kind of gnarly to look at, but that's our model this time. Any questions, folks, on getting to this stage? Okay, so now that we have this in play, let's take a look at the question. It said, how much of a 25-gram sample will remain after 5,000 years? And taking a look at this, I would probably say just about all of it. The half-life is 24,110 years. This is not even a fifth of that. And so we're not expecting this to decay by very, very much at all, even after 5,000 years have elapsed. But let's figure out just how much it's going to be. We'll write as our next step, amount of that plutonium-239, plug in a 5,000 here for time. What we're updating is this portion of the model now. Highlighted in yellow, it's going to be equal to 25 e to the power of negative natural log 2, 24, 110 times 5,000. So again, if this was on your paper on a final exam question, you've got it. You've got essentially almost all the credit. We still have to find a numerical value in the calculator, and that may be the more challenging step on this problem at the moment. So let's do that next portion carefully. Any questions at all so far, folks? Okay, for the calculator step, let me write out that strategy again of this is what it would look like in the TI-30X2S. Plugging all this in and by the red dot would look like a 25. Then it'll go e to a power, and then there'll be a big parenthesis. Next, for here, I'd go negative natural log 2, then division. We're dividing by the 24, 110. No commas though, that's kind of weird to get used to. Then we'll do an immediate multiplication, and that looks alarming because when we multiply here by 5,000, it looks like we violated order of operations, but we're actually okay. This 5,000 would multiply into the numerator, unless, I'm going to delete this in a moment. If you did this, it captures the 5,000 in the denominator, but without it, it's free to multiply into the numerator now. But if we want to be extra careful, there's no harm in associating like this, just an extra bracket of parentheses. But let's see how this comes out. I think this is going to be the harder one to approximate as far as the calculators go. So let me know if you're getting anything different, and we'll try to work it out. I need to make this a little bit longer this time. So for here, it looks a little bit different because it doesn't format like that in Desmos, unfortunately. I'll have 25 e to the power, negative natural log 2, divide by 24, 110, times 5,000. So after all that, our initial amount of 25 grams has turned into, let's see, 4 decimal places. They want a lot of accuracy. 21.6527 grams altogether. So again, barely decayed at all after 5,000 years. That's kind of remarkable, but that's because it's pretty stable actually. 24,000 years is what it takes for half of it to have disintegrated. So let me take a look at this. 21.6527 upon rounding. And this was grams. I don't know if that's a lot or a little, but that's how much is left. Well, any questions, folks, on the conclusion here? Okay, is that working out in the calculator, getting this value here at the moment? Awesome, glad to hear that. Again, it's not as high stakes on the final exam. It still feels great to get it down right, what we expect. But this is more, we're doing very careful work here because of Alex more than anything, can be just a real badger when it comes to this kind of work. So now there's a follow-up question to this. After 5,000 years, we still had a lot of the sample remaining, more than 80% it looks like. So now it's asking, how many years until only 1 gram of the initial sample remains? So we're asking, if we were handed 25 grams of plutonium-239, that's kind of a weird thing to have happen to you. We want to know how long until there's only 1 gram remaining. So to start this off, you might write A of t. This time we can't fill in anything here because our goal is to solve for time t. I set it equal to 1 gram. But now notice there's another way you could think of this. You could think of just a kind of weird numerical game where if you started with 25 grams and divide that by 2, that would have meant 24,110 years have elapsed. If you divide by 2 again, that's dividing by 4 altogether. Then this many years have elapsed, and we're at 6.25 grams. This is not a great way to solve the problem, but it's a good way to say, are we reasonable with whatever answer we're getting down below? Let's bump the power. After 3 half-lives have gone by, we're at 3 grams, and that's about 3/4 of a million years. Take another half-life. This is now 2 to the power 4. That's getting about where we're at. So we're expecting probably well over a million years in order for this to disintegrate to 1 gram, just by doing this weird experiment with half-lives. But now we're going to solve it exactly. At least by doing this, we have some intuition about where our answer is going to be. Not the exact answer, but close. So amount at time t. On this entire left-hand side, we go up to this model and just write it in. I'm going to write it in as kind of a special way. So by the red dot, it'll be 25 e to the power of. Now, r written that way is really kind of annoying. It's not a bad idea to leave it as r like this. And we'll substitute it back once we solve for our time t. So at the moment, it's 25 e to the power of rt equals 1. And let me just take a quick screenshot here. We'll use that in just a moment. Next thing we want to do is just divide both sides by 25. So it's e to the power of rt equals 1/25. Next step, you can do it immediately on this line if you prefer. Take the natural log of both sides. And then we get this wonderful cancellation right here. So e is gone. And we have r times t. Thought I selected the blue color. Let me try again. R times t is now natural log of 1/25. Last step, we're solving for time, so we'll divide by the rate r. And t is natural log 1/25 divide by r. But now this is a good time to make the substitution. And you don't have to take this trick, but if you're copying in a lot of stuff, but you could write it as one symbol, that's a valuable thing. It makes algebra look a little bit easier just to visualize. If it's easier to read your work is probably a lot more accurate. So now it's natural log 1/25 division by, you have to put in r at this stage. So r changes to negative natural log 2 division by 24,110. So this quantity, whatever it is going to be the answer to all of our questions on this problem. It looks concerning because of the negative, but the numerator is also negative since the input is less than 1. So now this is the moment of truth in the calculator. Let's see what we come up with. We were predicting over a million years to get to 1 gram of that initial sample. And plugging this in the calculator, it should look about like this. ln 1 divide 25, then divide again. And now we need to be very careful with this denominator. Order of operations can turn into a nightmare here without additional parentheses. So go with the parenthesis, negative ln 2, division 24110, then close that parenthesis, and we should be all set in that format. All right, let me give it a try in Desmos. And as always, let me know if you're getting something different, and we'll try to figure it out. You know, Desmos works, but let me do one slightly different thing. Oh, I don't want a new one. Sorry, give me one additional moment. Okay, I'll put it in the TI-83. This is kind of a rude thing to do because it's a banned calculator on our final exam. The only reason I'm using the TI-83 is to show this input, which will be similar in your calculator, the TI-32X2S, or forgetting that model number. So here I would be typing in for this portion, natural log 1 divide 25, then divide again, another parenthesis. Watch out for that negative sign. We have to literally use this whenever we're inputting a negative, like that thing. Then ln 2, then divide again, 0.2411 and close parentheses. Should look about like that in your calculator. You might have to scroll left and right to see the whole thing put in. And here's the moment of truth. It's not as long as I thought. Why did I think it was over 1 million years? I think I might have been looking at that a little bit weird. 100,000, 960. Oh, I put in an extra 1 right there. That would explain things. Should have been that as a half-life, and that takes us to just over 100,000 years is what I should have said. Sorry, I had an extra digit right there throwing off the numbers. It's also awful when these kinds of things are throwing you off. That makes it not helpful in the actual process. So our official amount of time is, let's see, we're rounding to 1 decimal place. So 111,936.4 years. That's still a pretty long time. We're all dust by then, but by then there'll only be 1 gram is the prediction. Forgot the value. Let me try one more time. 111,963.4 years. Thanks. So that's the amount of time required to disintegrate to 1 gram. So remarkably stable isotope, unfortunately, because again, that's the bad stuff. Well, any questions at all, folks, on getting through this one? Okay, I would say about this stage in the notes that we're in right now, we pretty much have completed the course. These are all of the main topics that you would see already on the final exam. I still have more stuff on here. And the reason for the more stuff is these remaining questions are mainly just here to support the ALEKS questions as well. We can think of them just as additional practice as well. We've seen some of these questions before. So let's try out a couple more and then we'll call it a day. Looks like we're getting back to money on this one right here. Then below I have a couple screenshots. These are taken directly out of ALEKS. I feel like these are the trickier ones that we see in ALEKS only because the formatting is pretty weird on this. So after a couple questions like that, I think we'll possibly be out of time. There's still one last question here. I'll leave it up to the class. We can solve it when we come back for the review, or I could just solve it and upload the solutions later on. So I'll ask folks how we feel about it later when we get to the end here. So next, let's try out this example number 5 and see where we end up. Well, it looks like it's back to money. It says $1,000 is invested at an interest rate of 5.4% per year, but they said it's compounded continuously. We want to know how many years will the initial investment be doubled? That's kind of an interesting question. If you see anything like this, how long until it's going to be doubled? Let's turn up to the handy formulas just to emphasize the strategy. You want this. Actually, let's just grab the whole thing. Why not? So anything asking directly about half-life or directly about doubling time, you might see a lot of descriptions on what to do in the ALEKS topic, but it boils down to always just this. So let me show you how I'd solve this question then. Thousands invested, but the initial amount is irrelevant to the problem. They're just trying to throw us off. The rate is what we want. It's at 5.4%. So we'll start by putting in R is 0.054. That's a decimal. Compounding continuously just tells us the handy formulas are the right ones to use because we're using the continuous model right here. So next, after how many years will the investment be doubled? This is kind of an exciting problem. It's really a freebie in ALEKS if you see this one. It's going to be this formula, doubling time will be equal to natural log 2, and the 2 here is for doubling time. If you wanted tripling time, just put a 3 here, and that's actually the right formula. That's kind of interesting in a way. Divide by 0.054. And that's your whole answer. We just need to import that to the calculator and get a value out. And let's see, it was at 5.4% interest. So I would assume the doubling time is a significant amount of years. I would expect over a decade. I'm not great at this kind of stuff, but let's see how close that is as a prediction. So go ln for natural log 2, divide by 0.054. And here's what we get. We want one decimal place, so about 12.8 years. And then we're done. That's kind of the best kind of question they could ask you on, say, a final exam. If you go through the old final exams, this has literally been a question on them before, and it was a really fast kind of problem, provided you had that formula ready to go. If the formula is not there, this is actually kind of a hard question to really get through. You would have to start by setting up A of t equals 2 times the 1000 and solve for t. So this is without, I'll just call them the handy formulas. If you have the handy formula ready to go, your answer is pretty much right there. We just put it together, and this is like a 2-minute problem at most. Well, any questions, folks, on solving this one? Okay, well, let's go down below. These are the ones that came right out of AlexNext. And these ones are a little bit longer, but they're not too bad either. Let me zoom in on this a bit more so we can read them better. One thing that Alex does that's a little bit weird is, instead of writing amount at time t, they're writing y equals. That's okay, it's still the right formula. It's just kind of a strange thing to do right in the middle of nowhere. So our model is turning into y equals a e to the power of RT. Our goal in these problems is to find the value of A, the value of R, and then just do a really fast follow-up question. So let's see what they tell us. The mass of a substance, they don't tell us what it is, that's kind of rude, which follows a continuous exponential growth model, is being studied in the lab. The doubling time for this substance was observed to be 17 minutes. Now that's really important information. We saw how that was very helpful to have doubling time formulas just in the last problem. So from there, I'd probably write doubling time is now equal to 17 minutes. So that's kind of helpful. But again, if you look at the handy formulas, this is even more helpful than it seems on face value. This gives us the rate R for the growth of this, or is this growth, or yes, growth for doubling time. It's going to be equal to the natural log of 2 divided by doubling time. And so the growth rate is natural log 2 divided by 17. And we've already found this value that goes right here. Next, we'll need the initial amount A, and they say an initial amount was the 82.9 milligrams present at the beginning of the study. So A equals 82.9 milligrams. Now for part A, all we have to do is write out the model. I can't really fit it in here, so I'm just going to rewrite it over here as y equals. First off, A value of 82.9. Base the exponential to the power of R is going to go right here, and we have it as natural log 2 over 17. And then times t. And Alex, you'd only be putting in the value that's in green, the value that's blue right here and here, but it's good to have this on your notes just so we're ready to go for the full model. Does that make sense to folks so far on this one? Okay, again, this problem could be a miserable experience. It could take us 15-ish to 20-ish minutes with explanation to get through it if we never used this formula right here. So the doubling time and the half-life time formulas, these right above, these are once again probably the most important formulas of chapter 6. Much like if you go through the Moodle document or Moodle page, most important formula in chapter 5 might have been, say, oh geez, where'd it go? Not that one. I'm thinking 5.2. There we go. Most important formula in 5.2 was this right here. This was the answer to a lot of questions, more than it even seemed like. This became something that we used over and over again in chapter 5. And these formulas were so handy in the same spirit as these ones. These are just as important to chapter 6 as those prior ones were chapter 5. So if you have these ready to go and memorized, you're going to be in great shape getting through these problems. And there's a chance it could be on the final exam. That's a great way to cinch the credit pretty rapidly for chapter 6 on the final exam as well. Well, we still have to go through our part B. It says, how much will be present in 5 minutes? That's not too bad. We're just putting 5 right here for time t and getting a value out. So we'll connect like this and say the answer, which will go here, will be 82.9 e to the power of that whole natural log 2/17 times the 5 minutes. So 5 would go right here. Then just jam all that into the calculator and we'll be in business with this one. Right, as before, let me know if you're getting something different. It's going to be 82.9 to start. Next, we need the exponential. It's under my natural log button, and same on the TI-32X2S or whatever it's called. Somehow I forgot the model number. I think your natural log button is just more on the top row-ish. Then inside here, it'll be natural log 2 divided by 17. Because the whole thing's being multiplied by 5, you can just go times 5, and order of operations does not get damaged here. The only way to make 17 be multiplied by the 5, making it incorrect, is if we had to add parentheses around it. So close parentheses here, and we're getting about 101.6, let's see, 101.6 to the nearest 10. Things are growing in this problem, so it makes sense that the initial amount, 82.9, grew to a value of 101.64. So this will equal to 101.6, and the unit here was milligrams. Let me just double check the numbers. Okay, well, we did it, folks. That's the end on this one. And again, this was actually a pretty kind of fast problem to get through, only because of the doubling time formula that we took advantage of to get through it. The next question is almost identical. It's just going to be a half-life one. So we'll practice a half-life formula on the next. Any questions at the moment before we try one other? Okay, so down we go. Same sort of thing, but we're dealing with half-life. It says a specific radioactive substance, which they would tell us what it was, but they don't have to. It follows a continuous exponential decay model. That's being indicated here with the base exponential, and it has a half-life of 8 minutes. So this is really, really unstable, it looks like. You might start by writing out from this information, lambda equals 8 minutes, which is the typical symbol for half-life. But if you don't use that symbol, that's okay. Our book didn't either. I'll use this initialization. Half-life equals 8 minutes to start. That was provided to us right here. That means we now have the continuous decay rate for this. R is going to be negative natural log 2 divided by your half-life. So that's the formula, and in our problem, it's negative natural log 2 divided by 8. So we have the value that's going to go right here now, only because they told us half-life is 8 minutes. Next, they say at the start of the experiment, 629.7 grams is present. Only because they said that that was at the start, we know that's an initial value. So A is equal to 629.7, and we're pretty much all set then. Your value of A is going to go here. Value of R goes into that location, so it should look about like this. The model is now Y equals 629.7 e to the power of, it's a half-life problem, so we expect a negative here for the growth rate, or excuse me, decay rate. So negative natural log 2 divided by 8, and the whole thing is multiplied by time t. So we've got a model, and now we just want to know how much is present in 21 minutes. So again, pretty fast problem actually. They're not asking too much out of here. The whole takeaway is working with doubling time and half-life. That's the major portion of these problems. So we'll take for our follow-up question, 21 minutes, just import it here. And it will look like this as an answer. 629.7 e to the, now let's write this out in kind of a calculator format. E to the power, it'll be negative natural log 2, divide by 8, then hit the multiplication key times 21. So this is what it would look like in the calculator. Bless you. No worries at all. And now let's see what we're going to get. Now the half-life was 8 minutes, and we're talking about 21 minutes later. And so we're going to have this divide by 2, about 300, divide by 2 again, to get about 150-ish. That's about where the answer is. A little bit less, because this is more than 2 half-lives. I would guess around 100 grams, with a pretty wide margin of error, but somewhere in that neighborhood. So let's take a look. 629.7. Then hit second, your logarithm button for the exponential. Negative natural log 2 for the half-life, divide by 8. Then just immediately hit times 21. Our value comes out at 102 point, let's see, we're going for nearest 10. Let's round up to 102.1 grams altogether. So this one, whatever the random substance was that it gave us, is 102.1 grams. All that's left after 21 minutes. And there's plenty of isotopes that really do disintegrate as fast as this half-life, or even much, much faster. Say the very bottom end of that periodic table, those things are disintegrating extremely rapidly. But we've got it, folks. That's the rundown of this problem for half-life versus the one for doubling time. Any questions at all running through either one of these? Okay, so there's one last question on this document. I would say this one is kind of the harder one of all of them also altogether. Almost kind of a challenge question, but not that terrible. But I'll leave it up to the class. Should we attend this one on our last amount of time? We've got about 8 minutes and some change. Or should we try this for the review? Or should we just solve it and dive into the review next time? It's kind of 3 ways to go. Give this one for the review. I think that makes a lot of sense because it's still an important problem. We'll come back on the review fresh and then tackle this one to start. That sound all right to folks? Awesome, good call on that one. So back to the document here. After we finish that problem, we'll think of it as for review at the moment. We'll go immediately next to this right here, the sample final exam. This document is pretty large, and I think these are screenshots. That's why it looks a little bit weird. But hang on, what class was this one? Math 1143, final exam, page 2. Oh, this was a real final exam. I think it was a PDF I put on the document. That's why it looks a little bit weird. We'll be solving these problems when we come back next class. Well, that's all I have for folks today. And congratulations. I think at this point, we have officially completed the course. The last question was just more of an additional challenge question on a topic. We'll return to that one as part of our review. We'll have a great afternoon, folks. If you have questions, as usual, I'll be available in office hours. Otherwise, I'll see you all in Thursday's class.